So we welcome you to the Lessons Learned workshop webinar today. And my name is Charles Swenson. I'm the MC for the Small Satellite Conference for this session today. Like to introduce our moderator, Anne Moran from JPL. Anne is a systems engineer at JPL, and she received her BS in aerospace engineering from the University of Michigan, and then her master's and PhD in aeronautics and astronautics from MIT. At JPL, she was a systems engineer for the Mars Cube 1 mission and the Near Asteroid Scout mission. She's previously been a lead engineer for the Team XC, which is a concurrent engineering team that supports small satellite mission formulation at JPL. Currently, she's an instrument engineer for the Europa Clipper mission. Before I turn over to Anne, I'd like to quickly just share real quickly our list of presenters here. So we will be going over these talks today in this session. We're going to give each of our presenters about a minute to give a brief synopsis and to remind people what their talk was about. If you haven't gone off and viewed the presentation, you can do that on the on-demand section of the Small Satellite webpage. And then we will go into a question and answer period. Those of you who are joining the webinar, there are two places down at the bottom of the screen, of your screen, for sending messages. I would encourage you to use the Q&A box. That is the way that if you want to ask a question to one of our presenters, please just type it into the Q&A, and Anne and I will see it, and we'll try and get your question routed and answered. As you do, type in your name and affiliation for your question. And with that, I think we will turn the session over to Anne and enjoy our webinar. Go ahead, Anne.
Thank you, Chuck. We're going to start with giving the chance for all the speakers to give a quick overview of what their talk was. So we can start with Debroshri Sadookan from NASA Glenn. You want to talk about Elbis.
Sure, sounds good. It doesn't look like I can start my own video though, but I can still go ahead. Hello, my name's Debroshri Sadookan, and oh, here we go. Good. Thank you. And I was the lead electrical engineer for the Advanced Electrical Bus from build to flight. So we had two primary objectives. One was to demonstrate the functionality of novel shape memory alloy activated retention and release mechanism and shape memory alloy deployable arrays in an on-orbit environment, and then assess the system capability to change a high capacity battery, distribute 100 watts of power, and thermally control the system in a low Earth orbit environment. We launched in December of 2018 as part of the CubeSat Alana XIX mission on Rocket Lab's Electron. So that was kind of a brief overview of what we were looking to do and accomplish.
Okay, thanks. Ariston Gonzalez from all the way in Manila, Philippines. Do you want to give an overview of your mission?
Thank you. Hello everyone. It's nice to meet you all virtually. I'm Ariston Gonzalez, one of the lead engineers from the Philippines Small Satellite Program. Our team's presentation was about the 57-kilogram microsatellite called Diwata 2, launched last October 2018 from Japan on board the H2A rocket. Its main mission is on Earth observation through multispectral imaging, and we have a demonstration of voice communications capability using the amateur radio band. Now, some of the key lessons learned that we would like to impart is on the importance of detailed structural mechanical models for finite element analysis, and the importance of maneuver modification using imaging observation results to improve the overall target pointing accuracy. Hope you guys found some interest in our development and results. And if you have any questions, we are happy to share our thoughts and insights later. Thank you.
Thank you, Ariston. And then the last speaker of the session that we have currently logged in is John Bellardo from Cal Poly Sloan. Do you want to give an overview of ISX?
Sure. So today, or this, I guess I'm here to answer questions, but the presentation was about ISX, and specifically it launched a little over a year ago now, and we were never able to make radio contact with it. And so we went through a failure analysis, and I walked through some of the more important points that came out of that particular analysis. And so that's what I'm here to answer questions about today. Thank you.
Okay, great, thank you. So to start, I'm going to ask a couple of questions that I'd like all of you to answer, because I think it would be great to get the perspective from different teams that with different levels of experience and different probably sizes of teams and even sizes of satellites that worked on it. So the first question I'm going to ask is, I'd like each of you to comment on the split between analysis and tests with prototypes for engineering units for environmental tests, et cetera, and what was planned for your mission and what, if anything, you would do differently. Ariston, since this was actually a fairly significant part of your paper and presentation, do you want to start?
Sure, okay. So just to be clear, regarding the question, you meant like if we have something that we want to change in terms of the plan going through another kind of small satellite development, what would we change? Is that correct?
Yeah, I guess comment on what was your split or approach to doing verification or testing via analysis? If you had a nice finite element model and did a lot of analyses and models versus building a lot of prototype equipment and using test hardware to do the same thing.
Okay. So actually with this specific satellite, Diwata 2, we already had quite a lot of, we incorporated quite a lot of changes from the way we've developed the small satellite because with Diwata 1, the sort of the predecessor of this satellite, we've tried to do just the directly sort of a EM-FM model, if I might say. So we have some engineering model prototypes of our modules. And then for the structure part, we had sort of a limited iteration chance to do the structure. So what we did is to, of course, do some design in CAD and then imported that to the FEA software. And then from there, once we had some results, we already fabricated the sort of what we feel like passes the qualification requirements. But from that initial sort of like a fast track simulation verification, we've noticed that the actual vibration results had a huge difference from the software simulation. So with that, we had to go through some number of mechanical refabrication of the prototypes. So coming to Diwata 2, what we've did is to sort of look back and check what we can improve in terms of the simulation so that we can reduce that number of refabrication of the mechanical parts. And it was quite effective. So we've used a more accurate model in terms of the, what do you call this, configuration, meaning instead of just using simple slabs of plate to represent the structure, we actually incorporated all the intricacies, for example, the isogrid and whatnot. And for us, it proved to be quite effective because the final vibration result was actually within 5 hertz on the first 2 modes. So that was quite effective for us. Now, on the functionality side, in terms of the electronics modules, I think this is something where we believe we can still improve on. So we have engineering model prototypes for doing the various functionality tests and attitude-related tests. But I think we have a lot of things that we have not quite modeled yet on the ground. Although there's a lot of challenges on that. So I think that's one of the things that we would want to work on more. Did that kind of answer the question? I felt like I went through a little bit on a side.
No, that was great. I noticed that you had a lot more effort in modeling than I'd seen with other missions. So I thought that was very interesting. It seemed to work out pretty well for you guys. Thank you.
Thank you.
Debrochery, do you want to give an overview of what the approach between analysis and modeling and test hardware was on Albus?
Sure. For Albus, we, I think, did more modeling with the structural standpoint. We had a FEM and kind of went through that more in depth of an analysis. But on the electrical side, we definitely did more of the engineering model approach to then rebuild and kind of test and break kind of kind of testing and stuff like that, and then eventually build the flight model. And I think if we had to go back and change anything from the electrical side, I would say I think I would want to do more of an integrated analysis. We didn't really have many of our connectors or anything like that modeled structurally or anything. I think I would have liked to do more of a system integrated model and do some vibes, some power transfer calculations and stuff like that versus doing the testing. I think that might have helped us in the long run.
Great, thank you. And John, what about on ISX?
Yeah, so ISX was similar to some of the other missions that we have done in that we always have a relatively high fidelity CAD model that we use for fit check and component checking. As was previously mentioned, we're not as good at getting all the wiring harnesses and connectors in there. And so that's something that we're working on going forward because that ended up being a little bit of a challenge when we got to the engineering build. Past that, for modeling, we will model if it's a new component or a new subsystem that we don't have familiarity with before, or if our back of the envelope calculations indicate there might be a problem, then we'll spend more effort on the modeling side. But barring that, it's all sort of flushed out with our engineering unit and our not really the flight unit, but with the engineering unit. And we actually have a third flat sat without the structure that we use largely for electrical and software testing as well.
Great, so I have one more follow-on question to that, but first I'm going to remind anyone who's online who has questions that they want to bring up real time, please use the Q&A window on the bottom of the menu. You see a Q&A box and a chat box. Please use Q&A and we will address your questions as we get to them. So my follow-on question is for people who had an EDU or a flat sat version of the test model, as John, you just mentioned. How is the fidelity compared to flight, and how important was that in doing, if needed, a failure assessment of your spacecraft?
Okay, I guess I will go first. So the flat sat is basically electronically accurate. And we use that primarily in early and mid development cycle to troubleshoot our electronics and to test our software. For flight, we actually had a almost identical copy in lab that we use both for practice commanding prior to uplinking and for troubleshooting, figuring out the failure analysis. A lot of the branches in the fault tree that we came up with, we were able to actually run tests on our ETU here in lab and either rule them out or provide supporting evidence that they may have contributed to the failure. So I'd say that was an important part of our fault analysis. It's also an important part of our normal operations.
Great. Did Brochery or Ariston? I think I saw Ariston start to unmute.
Oh, okay, sorry. Okay, I'll go next. So that is actually a really good question. And I think based on the flight data that we already have for the past year and comparing the performance of the various subsystems and the specific modules versus what we're expecting on our ground testing via the FlatSat or the Table satellite, I think there's quite a lot of difference in many other in specific areas. So for example, in terms of the performance of attitude sensing and the actuation using the reaction wheels, as much as we try to model the errors or the drift and other sources of inaccuracies, I think there's still quite a lot of nuances that occur in space. So maybe to make it short, a very specific module that I want to share is the magnetometer. So on the ground, we can kind of do some calibration on what can be expected in terms of hard iron or at least electromagnetic emissions of the system itself, and trying to contain that within the environment where we are testing it. But of course, without, for example, a Helmholtz cage, there are still some occurrences of magnetic noise or sources that we might not experience out there in space. So we try to sort of eliminate that in through a simulation of or modeling what is the environment we have and then sort of canceling it out. But more than that, what we can't really model is, for example, in flight, there are some occurrences of or fluctuation of the magnetic field probably, or maybe due to the solar activity. So these kind of things were not incorporated into our model on the ground. So the in-flight results are kind of different, and the maneuver should be sort of change or tweak so that we can anticipate this kind of changes. And that's just one thing. But on the positive note, some of the things that we've tested on the ground, for example, in power, remained quite accurate out there in space, meaning it's performing to the expectation that we've had. So in that sense, there was a lot of benefits in terms of doing that kind of power-related tests using the FlatSat on the ground, because we can expect if there's some anomaly happening out there, something that is not expected in terms of just as simple as the power draw. So these kind of things.
Great, thank you. And Debauchery, did you have anything to add?
I think for us, it was really close to what John said. We had electronically accurate FlatSat, basically, we could use to troubleshoot an EM model and in flight. So once we shipped it off, we had a complete identical copy with us. As far as the structures go, if we needed to rebuild, we wouldn't have any of that hardware as a copy, but a lot of it was mainly the electronics, so we could troubleshoot throughout the process.
Great, thank you. We have some attendee questions coming in, so I'm going to start going through a couple of those. So one of them is, what is the most important systems engineering approach you think you can do for your mission to ensure mission success? You can boil it down to one. I believe that question anyone can answer.
Okay, I'll take a throw my hat in the ring on that one. Well, it's not necessarily a systems engineering approach. We've found over ISX and other missions that we've had the most success when we've been able to have an extended period of spacecraft functional testing just in lab, where you have 2 or 3 months to operate the spacecraft as you would on orbit and work through all the kinks that might come up. The missions that had that longer period of time tended to be more successful missions.
Yeah, I can completely echo that. We did a full functional test after every major environmental test that we did, as well as various points in our development, just to make sure that our concept of operations would work as intended, and fixed any hiccups that we had along the way. So definitely verifying and validating along the way, and making sure that what you intended it for it to do along the process is really important.
I also agree with them. And just to add, I guess, for us, we would really advise to just keep on creating as much test case scenarios as you can, so that you can go through at least what you expect or not expect for it to happen, and then provide sort of a fix before you even launch it into space.
Okay, great. While we're on the subject of testing and flat sets, there's a question on, did you model power and thermal characteristics in software, or were you able to use flat sets for power and thermal testing?
So I can go first. For us, we did power mostly with the flat sat. Thermal was mostly modeling. We did do a final thermal test with the entire buildup, and then a few smaller bell jar kind of thermal tests with some of our electronics. But thermally was mostly modeling, and power was mostly testing on the bench.
Okay, so for ISX, power was also mostly testing on the bench. Thermal, based on the ConOps, was not a large concern for us going into it. So we just verified that through some testing on our engineering unit.
With Tiwara 2, it's very, very similar. So we use our FlatSat for the power test, and then we use Thermal Desktop for the thermal aspect of the design. And then we just verified it using the thermal vacuum chamber test.
Great. Okay, we're gonna change gears a little bit. So we've got a question from Andy McKenna at the Naval Research Lab. This is a question again to all panelists. What is your take on the balance between COTS, commercial off-the-shelf components, and more space-hardened or space-qualified components, especially in terms of cost savings?
Okay, I can go first, I suppose. So we have a long history of using COTS parts in all the CubeSats. That we've done over the years. We have tried to find parts that have higher ratings, right? So maybe industrial grade parts, because they tend to do a little better. But in general, we have not gotten any or used any space specific parts. And for the most part, it's worked out well for us. Obviously, the parts are a lot cheaper. I'd say the one caveat is, when we look for parts, there's certain technologies that we understand hold up better in the space environment. For example, some of our memory is a FRAM type technology, and that ends up being more robust than some of the other memory storage. So we try to understand the technologies and pick the COTS parts that we think are going to work better, but we don't actually go to full space rated parts.
Great. Thank you. Debosher, go ahead.
You're fine. For us, we did mostly custom, mostly because that's what our project was set out to do a next generation power supply and shape memory alloy technology that hadn't been flown. With that came some challenges. We had to do solar panels custom that fit those shape memory alloy and stuff like that. I think it added complexity and more points of failure. But I think it really depends on your mission and what it is you're trying to achieve. And like John said too, with COTS parts, like space rated, we didn't really go that far into it. We used just regular rated parts and everything. And so I think it's a balance of what your objective is versus can I just use this part that's known to be effective and the reliability behind it.
I agree with the debauchery. So it is very important to evaluate the criticality of your mission and which parts really contribute to achieving the 100% success of your mission. So at least for us, we're relatively new to the development of small satellites, but at the very least, we do value putting, what you call this, as much as possible, space tested modules for the critical or mission critical parts. But actually, we do have a lot of COTS parts that we just call this subject to the various qualification tests. But I agree, the trade-off in this kind of scenario is the cost as well, and the time you will need to spend to evaluate those COTS, or also again, if it has a huge impact on the achieving the mission success.
Great, thank you. And a quick follow-on question to that, specifically on radiations. This comes from Johan Leitens from Lens R&D, and I apologize if I'm mispronouncing your name. Many satellites refer to lifetime by mentioning the total ionized dose of resistance of components, whereas there's not necessarily a lot of failure due to radiation, and most modern digital electronics are more sensitive to single event upsets or latch ups. How did each of you verify the desired lifetime, and did you do any specific radiation related analysis or testing? Ariston, do you want to start?
Okay, I'll go first. So for us, admittedly, we have not done a thorough sort of a operational lifetime of our satellite in terms of the electronic side. Well, of course, we can project sort of the orbital lifetime, but at least on the electronic side, we have not done a very thorough analysis of each of those components. But what I can say is that we conducted limited radiation testing to critical parts. For example, the power control unit and the main satellite computing unit. And lastly, of course, the mission instruments. So these are parts that we believe that should be at the very least tolerant, for example, to SEE or single event errors, or more importantly, to latch up errors. So for us, we conducted TID tests, for example, on the optics, so that we can ensure that there are no degradation in terms of the performance of these multispectral imagers. And then for the power control unit, we want to make sure as much as possible that it does not fail, because once this power control unit fails, obviously everything fails. So this kind of analysis, and we rated them for at least for our initial plan is just for it to pass 3 years kind of TID, so around 40 kilorad. So yeah.
Debauchery, did you have anything you wanted to add on radiation?
From Albus side, I don't recall any radiation analysis or testing that we had done for our CubeSat. I echo in doing the calculations, and points of failure would be very important. I personally didn't have a hand in that, so I'm not real sure if our team had done calculations prior to my joining the team, but that is a very good question.
Sure, and I can chime in that we didn't do any specific radiation analysis for ISX. However, we had flight heritage on a number of prior missions with very similar electronics. So we have a sense for how long they last in orbit, and we weren't worried about meeting the 6-month mission lifetime minimum for ISX.
Thanks. And then I have a couple of questions that I'm going to hopefully combine into for John specifically on the ISX failure. So there are a couple of questions on the fault tree analysis and things that weren't necessarily mentioned in your paper, or if you went down those paths. So did you try to get any imagery, such as sat-squared imagery, to see if the antenna might have actually deployed, look at failure due to radiation of a solar event, or did you look at failure due to a ground station? And if you could just comment on your process in doing that fault tree analysis, I think that would answer a lot of those questions.
Sure. So let's start with the antenna for the fault tree discussions and the documentation. The discussions I recall in the documentation went back and looked at for the paper and the presentation. I don't recall discussing any kind of optical imagery to demonstrate that the antenna did or did not deploy. That was the first question. I'm sorry, I'm trying to find so the next one was the failure due to solar radiation event potentially. Actually, can I get back to that one? I actually need to go look at the fault tree and see that was in there. I don't recall off the top of my head.
Yeah, that's.
Sorry. And what was the third one?
The third one was, did you consider the ground station element? Because I think your paper mostly
Yes.
focused on the spacecraft itself.
Correct. Yeah. So we did, and it was not a likely scenario given the fact we were operating other spacecraft with the same ground infrastructure at the same time. So we didn't spend a lot of time considering that. Plus, there's a number of amateur tracking stations that folks across the world who like to track satellites and post the results. And none of those were able to spot ISX either.
Okay, thank you. And there's another question that I think I'd like Debauchery to start with on is, how is the process to capture and manage lessons learned, specifically keeping them present throughout the development life cycle, and with different teams? Because I know in Debauchery, I think it was about a 5-year development lifetime.
Yeah, our CubeSat development took quite a bit of time, a lot of hiccups along the way. And I might have mentioned before, yeah, I joined in, I think in year 3 or 4 of this, I think it was year 3 of the development cycle. A lot of the lessons, I think it's important to capture, especially with turnover from team members on a project that lasts so long. Kind of the history behind it is, and a good way to capture that I would even say just keep a spreadsheet of lessons along the way after each milestone. So as a NASA-driven project, we followed the entire systems engineering life cycle. So after every milestone review, I think it would have been good to capture some lessons and things for future either team members or even for our paper. We spent a good amount of time going back and kind of thinking about what happened 5 years ago, and that was a little difficult, but there were a lot of lessons along the way.
I think, John, since you work with students a lot, and I think you also mentioned this in your presentation, did you have anything you wanted to add?
Sure. The way we've tracked lessons learned has, I'd say, evolved and hopefully improved over the years we've been doing this. So the current system we use on our CubeSat missions is to sit down and generate a list of the lessons learned sort of at the end of the mission. That works okay if your missions are only take a couple of years. For the longer missions, it's really more important to track them on a major milestone basis instead of the end of the mission. And it's something that we're still working to improve on our spacecraft side. And the other trick, of course, is convincing people to go back and look at the lessons learned that have been documented. It is a key part of that process as well.
And Ariston, if you could comment from the perspective of kind of having lessons learned from previous missions, how are those able to be captured, and was there a lot of team turnover that you experienced?
Yeah, this is actually an interesting question because this is one that we're currently going through consistently from Diwara 1 to Diwara 2 and hopefully forward to the next series of satellites. We try our best to do a well-managed documentation, but it's easier said than done actually. But we try to use tools that are collaborative in nature and that has a more user-friendly interface, I would say, because sometimes there's a lot of information that we can pass down, sort of, so to speak, and a lot of this information are kind of hard to just concisely distribute. So we try to compartmentalize them. So for example, on software source codes, many of us, of course, use, for example, Git tools, and we use very similar tools, and we try to do our best to have an accompanying documentation for this kind of software. But that's just the software part. So we also have documents for the mechanical, for the other subsystems. So we try to compartmentalize them and try our best to manage them. And on the in-flight data, we try to keep a database of all the raw data, flight data for archives. But we also separate the process ones and incorporate accompanying pointers that would be helpful in terms of lessons learned. Yeah. So basically, that's what we've been trying to do so far.
Okay, thank you. Okay, can each of you, and I think we can start with Ariston, how much environmental testing did you do, and is there anything particularly with regards to vibration or TVAC that you might have done differently?
Okay, so for us, the top important environmental test that we've done is, first, of course, is the vibration test. And then second, we have a thermal vacuum test. And then the third one, the shock test is, I think it's not applicable to all kinds of satellites, small satellites, because for example, on Cube satellites, mostly they're being deployed through a deployment system. But for those that needs to be sort of released explosively, literally, into orbit, you have to have this kind of test. I would just like to focus on one thing for this response is the vibration test. So it's very important for us because this would define the acceptance of our satellites. I would say that this is applicable to most, but for us more so. And sorry, the last part was what we are or what we would change if we had the chance. Is that correct? Something like that.
Yes.
Okay. So that's a very interesting question. I don't have a good response on the top of my head, but I would say we would want to make sure that we have the not exactly the vibration test, but the accompanying system level kind of functionality tests that we can do. Because once we have, for example, a flight model that is ready for, let's say, vibration test, we want to do a thorough post-evaluation of the functionality. So sort of like a sanity check if it's still performing up to speed. But the way we're doing it right now, we have a limited version of the initial rigorous test that we have, functionality test, for post FM vibration tests. This brought about by the fact that, at least for our case, we have sort of some limitations in terms of interfacing with some of the functionalities once it's already sort of stowed into the final configuration. We can still do the important tests, at least what we think is important. If we have the chance, we would want to expand that to the more comprehensive tests that we are doing when it's not yet done with the FM vibration.
Great, thanks. And Debauchery, can you comment specifically on TVAC or thermal testing? And question still stands, but I think for Albus, it was an interesting situation with the TVAC test in particular.
Yeah, so for us, for TVAC, we did a lot of the testing with our development and engineering model, but we did bake out, of course, for our flight model, but because of a lot of our delays and anomalies, we didn't end up doing a full functional and performance test of the flight unit under TVAC. And I think if we had to go back and change something, that would be the one thing I would add back.
Okay, John, did you have anything you wanted to add there?
I'm just going to echo what was just said. The functional tests in TVAC we found are very useful, and they usually have to go beyond what's required by just the bakeout profile from the launch provider. But if you can spend a few days in TVAC and do functional checkouts, you can catch a lot of problems that would otherwise occur. In fact, we caught one with ISX where we had a thermal expansion issue on a trace.
Okay, another question we have is that I just lost again. Sorry, the chat window is jumping around a little bit. So especially for those of you who heard your paper was more of a failure analysis, once launched, obviously you were not able to probe using scopes or anything. You have very limited ability into what the spacecraft is doing. Was there anything you specifically planned for in terms of understanding an anomalous behavior and how to recover from anomalies? And again, there's something that you would, having gone through it, is there something that you would change or implement in the future? So Debauchery or John, if you wanted.
Okay, yeah, I can start. I'd say there's nothing. So when we design our ConOps and our missions, we have been sensitive about uplink performance and as to how much we're going to have, because we've seen cases where we might not get good uplink for a couple weeks, or early on, this is maybe a decade or more ago, there were some interference issues with some of the radios we were using that made uplink challenging. So for the most part, we try to design the spacecraft operations so that we can get as much insight as possible, assuming very limited uplink. And ISX was no different in that regard. Unfortunately, because there was no transmission from ISX, no downlink, we weren't able to take advantage of that facility.
Yeah, from an Albus perspective, we built in extra data that we would get when we did download our data from passing on the ground. But because we lost communications with our CubeSat after a short few, like about a day or so, there isn't really anything else, like without communications, anything else we could have built in to know what was going on with it that I can think of at the moment.
And Debosher, I have a specific question for you because your recovery of the spacecraft unfortunately happened during a government shutdown. Were there other, if you had the resources available, are there other assets like other ground stations besides Wallops or other things that you would have tried in order to recover the satellite?
Well, that's a really good question. I'm not really sure what else we could have tried other than being able to be there and try to troubleshoot with the Wallops team, have our comm lead go down and kind of, try to work different. I mean, we were specifically built to work with the Wallops ground station. I'm not too familiar with that setup to know if there was another ground station we could have used personally. I'm sure there were some options that we could have looked into. But I think, yeah, with the government shutdown, we couldn't really, put boots on the ground and kind of figure out what was going on real time until it was too late.
Okay, so guys, looking a little bit more toward the future, do you have general opinions on viability of some of the newer electronic components coming out? Or companies like TI or Renesas or others that are offering low-cost, rad-tolerant products. Do you see these as valuable alternatives to quote-unquote standard COTS parts? Do you think they're overkill? Do you think there's a lot of risk involved? Could you comment on those a little bit? I'm going to call on John to start.
Sure. So I guess the short answer is I don't think we've looked seriously at them yet. A lot of our component selection, especially on the electronics that we reuse from mission to mission, was done a while ago. So we haven't really gone back to do a trade study with those components. We absolutely will include them in trade studies at the appropriate time. In terms of the risk, we've been using COTS parts for a while. And so we felt very comfortable with that. So I would feel comfortable, using the parts if they made sense from a trade study standpoint.
Okay. Ariston or Debauchery, do you have specific thoughts on those?
Yeah, I would definitely say I wouldn't preclude them from doing a trade study, but I think, weighing your options with the new parts and what's known about them versus, what you already know is important. But I'm not too familiar with what's out there at the moment with those parts to really comment any further.
For us, I would say we're on the stage where we're a little bit aggressive in trying out some of the COTS parts and evaluating them. And the challenge, of course, is again the reliability of these parts in terms of the space environment test. So specifically, again, I think we would have to go back to the radiation performance, because for example on the temperature side, I would say there are already a lot of COTS part that could hit certain temperature ranges that we typically call this experience in especially in low Earth orbit, and there are a lot of ways to mitigate the thermal effects of the thermal cycle in space. But on the radiation part, the first thing that's very difficult, of course, is that no manufacturer so far, in terms of the general COTS parts, are doing this kind of test, because that test is destructive in nature itself. So you couldn't really, just subject your parts and qualify them. So for us, we have to do this kind of test on our own. But the challenge again on I think this sort of a warning, even though some of the parts that we or you will test would pass TID or some low dosage radiation test, I think there's still a danger that it's not a good representative of the whole product line that you're choosing, because it might have other dependencies. So for example, maybe the fabrication source, the wafer level source, or maybe the lot source. There could be some variance in terms of the susceptibility to radiation effects, or these kind of things. So I would say a good approach, if it's possible, is to coordinate with the manufacturer. If you can have a communication line with them, so that you can explore more about that product and what they really think it can provide in terms of resilience to this kind of space environment effects. That's all. Thank you.
Okay, thanks. And it looks like we have Sarah Rogers joining us. Sarah, if you have mute and video capability, then if you want to give about a minute or just a quick overview of your mission, Phoenix, we can bring you into the conversation as well.
Can you guys?
And we can hear you and see you.
Okay, awesome. So Phoenix is a 3U CubeSat developed by students at Arizona State University to study urban heat islands using infrared remote sensing. So we have a payload, which is a fluoro-infrared camera, and the objective is just to take different pictures of different cities all over the US to study this. So Phoenix actually deployed from the ISS earlier this year in February and is now in orbit. That's Phoenix in a nutshell.
Okay, great, thank you. So we're going to continue with the questions. We're going to be wrapping up in the next 3 or 4 minutes. So the first question, Sarah, if you want to go first, the question is so especially for the missions that did experience some amount of failure on board, is there a plan for a follow-on mission, or is there other plans for any technology that you were planning to demonstrate?
Right now, there's no plan for a follow-up mission to Phoenix. We were funded as part of a student flight research opportunity from NASA, but ASU is working on trying to get more student-led CubeSat programs going at the university. So potentially there could be a follow-up, but not one right now. And Phoenix was mostly meant to be a technology demonstration for using commercial off-the-shelf parts to still do this kind of very high fidelity science using a CubeSat platform too. So that was kind of our technology demonstration of the mission.
Okay, Debauchery or John, did you have, I think I'm going to start with Debauchery on because you had 2 like fairly interesting, exciting technologies that you were demonstrating. Is there a plan to fly those again?
Not at this time. Oh, I'm sorry. Sorry.
No problem.
Right now, we don't have any plans to. The shape memory alloy part we did prove with just deployment and being able to hear our CubeSat, but as far as the power system go, right now we don't have any plans to refly.
And John, what about ISX?
Yeah, so right now we don't have any plans to refly ISX in its current state. We're always thinking and discussing it, but we have no concrete plans.
And Sarah, I had a question for you that was asked a little bit earlier, but I'd like your input on it. Because you worked on mostly a student team that lasted many years and many semesters, how did you capture and manage lessons learned across the development lifecycle and between different teams?
Yeah, so I guess mostly, so we do have some lessons learned that I've actually captured in a podcast, which you can find access to on the Phoenix website. And so that's 5 hours of us just talking about our experience and lessons learned. And even though there was a very high rate of student turnover, there were several people who stayed over the years. And so they've kind of absorbed all of the lessons learned along with me. And so we've mostly captured things as we've documented our progress in memos. That has been a huge part of it is just capturing everything in documentation. And then I'm planning to release my everything that I've absorbed over the years in kind of a history document of how Phoenix was taken from a paper concept to a flight system, but I have no idea what I'll be done with that yet. So
Fair enough. And then if you can do it in about a minute, can you give the story of Kapton saving your spacecraft?
yeah, so basically we had this tolerance issue with our deployment switches and the NanoRacks deployer. And so our deployment switches weren't actually inhibiting our batteries. And we wanted to find a way to fix this issue without having to take anything apart mechanically. Because if we did that, we'd have to revive and do all of that. So what we ended up doing is we cut really thin strips of Kapton tape and we laid them over the roller part of the roller switch and then the arm of one of them, because really all it needed to do was just to press a little bit more in order to actually click the switch. And that actually worked. and it flew like that and it deployed and the battery was full, so it didn't turn on at all during launch. So tape really does solve all of your engineering problems.
Great, thank you. Well, we're nearing the top of the hour, so thank you. Thank you to all the panelists and all the participants who asked some really great questions. I had a lot of fun. I hope you all learned something and had a lot of fun as well. Chuck, did you have anything to add?
Well, thank you. Let me take it back and thank you, Anne, for expertly running our panel. And once again, to thank all of our panelists. We've had a couple hundred participants online and a lot of questions. Hopefully we've addressed all your questions as best we could. And thank you very much for attending this webinar on lessons learned.